I hope that you're all here to learn about GUI programming and in Go. Um, that's this room. So, hi, my name's Chris Waldon, and I'm here to talk to you about a GUI toolkit that I help out with called GU. It actually has nothing to do with the GNOME input-output library that is spelled the same way. So I'm just going to get that out of the way. Um, but I'm honored to be here with you. Thank you for coming. Let me tell you what we're going to do today. I'm going to briefly mention myself, and then we're going to dive right into what is this thing and why is it interesting? And then I'll give you some options if you want to learn more. I am one of GUI's maintainers. I'm a freelance software engineer, and I make my money building features for clients who want to consume this technology. I'm also a dad and a husband, and you can see the adorable people I belong to up there. And I have 3 cats, some of whom are more photogenic than others. But I got started with GU maybe 3 or 4 years ago, and sort of entered its event horizon. I got sucked in, and now I help maintain it. I didn't start it though. So what is it? What are we here to talk about? It's a way to build fluid and beautiful interfaces that are going to run basically anywhere. And we're doing that in Go for a number of reasons. So let's look at some examples of things built with Go. If any of you have heard of Tailscale, their mobile Android application is a Go application. But also there's a company called Play-Doh that makes casual social games, something, classic card games that you can play with your friends online, and also a number of other games that they've created. And traditionally they've been a mobile platform, but they've recently built a desktop launcher for their ecosystem atop Geo, and that's what's depicted here on the right. But people use us for all kinds of stuff. Some other more exotic things. In the background here is Sointu. It's a music synthesis application from the 4K demo scene. So 4K demos are competitions to pack the most interesting audio-visual experience you possibly can into a 4 kilobyte executable. So people do all kinds of crazy optimizations to pack shaders and music and everything they can into these tiny files. The executables are like self-decompressing and all kinds of craziness. This application lets you develop synthesized music instruments built from a number of primitives and then compose tracks built from those. And then it compiles those instruments and their music into a minimal assembly language representation. So, you're talking like a few hundred bytes to describe the instruments and music that you have programmed. It's kind of wild. And this GUI for doing that is built atop Go. And then in the foreground is Go Trace UI, which is just a Go programming language execution trace viewer that is built with Go. And it's fun because it can view itself, like many fun observability tools. You can trace the tracer. But what are the goals of our approach and why is it interesting? Use a community-driven project. It was started by an individual named Elias Snauer. He's a Danish gentleman. And our work is in the open, driven by a community that is not really affiliated with a company. We're a collective of individuals who are working to try and move the state of the art forward in GUIs. And we work hard to enable anyone to participate in that. So you can actually participate in our community without any account anywhere. If you have an email address, we facilitate contributing via like mailing lists, and you can create issues and stuff by email. But if you're more comfortable with GitHub or SourceHut, we're sort of bridged to all of these platforms, and so you can participate. However, we're cross-platform. You can write a GUI application and run it on Linux, of course, on Windows, on macOS, on Android, on iOS, on tvOS, on Android TV, compile it to WebAssembly and run it in the browser. We run a lot of places. There's even sort of an experimental bare metal thing that we can do. We're accelerated. Everything in GUI is built on your GPU, or if you don't have one, on your CPU. So we take advantage of what efficiencies we can from the hardware, and that just happens by default. You don't have to opt in. You don't have to do something special when you're designing part of your interface because this part needs to be fast and the rest of it doesn't. That is the default. We are accessible. We decorate the interface with metadata so that you can traverse it with screen readers so that you can find elements programmatically. This is an important thing. It's something, that enables a lot of users who otherwise wouldn't be able to use software. It's also an area we could use some help in because it's complicated and every platform is different. But it's very important to us. We are versatile. I tried to kind of cherry pick a collection of applications from a lot of different domains to show you that there's a lot of different things that you can choose to build. We try to be very efficient. Our applications start really fast, a couple hundred milliseconds. They run with relatively low resource requirements, and they respond to user input with low latency. And finally, we are in the public domain. Our project we don't own it. We don't even claim copyright to it. You can do whatever. Take it, build with it, adapt it to your needs. That'd be great. It is a platform for everyone. So let's talk about kind of at a technical level, what makes this interesting and different from the many other GUI options that are out there. But to do that, we kind of need to talk about like what a GUI is. And many of you probably know these things, but I will briefly go over sort of the high level of what a GUI has to solve, right? A GUI wants to present something to the user. We can talk about this slideshow as an example, right? It's essentially a rectangle of pixels, and those pixels all have a color. And a GUI needs to give you some way to draw that rectangle of pixels, but a rectangle of pixels by itself is not a GUI, it's an image. You can't do anything to it. You need some extra layers in order to make it useful. You need to augment it so that the underlying platform knows some things about it for reasons like accessibility. Where is text? Where are buttons? What can you do with those pixels? And then the third element is more about when the user interacts with your rectangle, what part of your application code is actually responsible for dealing with it. There's got to be some mechanism to, when I press a key or touch a screen or click on the mouse, how does that event get routed to the widget that's, say, visually underneath it? And so every toolkit has to do something to address these three things. And there's a lot of toolkits because there's actually quite a few strategies that you can employ to build these structures and interweave them. And so in GUI, we do all of this via a unified construct that we call the operation list. So in GUI, when you go to present a frame, you populate this operation list with instructions for GUI that describe these three aspects of your GUI in a unified paradigm. So there's drawing commands. We can say, hey, I want to work with this area of the screen and I want to fill it with a color or an image. But you can also say, hey, the area of the screen I'm working with is a button, or it is text that says whatever, or it accepts keyboard or touch or pointer input. And all of that is encapsulated in operations. So you can think about GUI at its low-level API as a sort of virtual machine with an instruction set that describes GUIs. Every frame, we build an operation list that describes that frame's visuals, that frame's inputs, and that frame's metadata. But just because we built an operation list doesn't mean we actually have to execute all of it. We decouple these steps so that we can take advantage of redundant structure within consecutive frames. Last frame's operation list already did the work to display this thing, so we don't have to do it again necessarily. So in this way, you think about building your GUI, composing your GUI on sort of a frame-centric way, but it's quite cheap to build an operation list. You're not actually executing any commands on the GPU at that point. You're just describing what you want to happen. And then if it's already happened, it doesn't need to again. So we also provide a higher level API that you don't have to use. In fact, there's entire projects and toolkits that are using only GUIs low-level constructs, and they have their own layout systems and their own widget libraries. And some of them are like the data visualization tools that use GUI as a output platform so that they get all the cross-platform benefits to, just display graphs that are interactive. But we do provide a set of layout primitives and a set of widgets that you can use. And the paradigm that we use for that is immediate mode layout. And so what this means is we actually, frame to frame, do not track the size and position of anything. All of that math is redone to generate each frame. And that sounds a little crazy because it seems like it would be really, really inefficient. But the math to decide how to partition a rectangle is a bunch of addition and subtraction. It's very, very cheap. And the alternative would be tracking the size and position of everything. And then if something has to change its size in response to either the window resizing or some piece of data within the UI changing in a way that affects its size, you have to implement sort of a outward cascade of, okay, we got to update everywhere that we're tracking size and position to be consistent with that. There's a lot of complexity in doing that. And it's very easy to screw up writing a layout or a widget and end up with bad sizing. But when you approach it from this way, it's very, very easy to respond to changes in size. It's very easy to respond to changes in content within your layout. And it's not very expensive to do it. So we use a constraint and dimension system inspired by Flutter, where every widget is given a description of how much space it must use and how much space it can use, your minimum and your maximum. And they're both described as just a point that is meant to be the outer bounding box of some rectangle. So here on the right, I have a visualization that you can see these two text widgets, and their actual size is a green rectangle. Their minimum constraint that they've been given is sort of purple, and their maximum constraint is red. And I'm manipulating their minimum and maximum constraints, and they're obeying that when I drag the purple rectangle here so that it exceeds their green size. You can see that their size is forced to increase to match. And when I drag this red rectangle so that it compresses the green, the widget is forced to resize it. It's no longer allowed to exceed that space. And this system allows you to build surprisingly sophisticated layout primitives by using a pretty simple set of rules. So GUI uses this system to build flex boxes and lists and disclosures and all sorts of things in a consistent way. So the high-level API is cool, but the low-level API lets you understand how sort of different the approach that you take when you want to build a widget is in GUIs. So I want to walk through building something like this button in GUIs primitives. So you can see it's just a simple button. It has a simple click animation, and we'll walk through building it one step at a time. So to do anything, to manipulate any part of your screen, you have to select that part of the screen. We call it clipping. So you can clip a lot of shapes. You can clip rectangles, rounded rectangles, circles, ellipses, or arbitrarily complex paths. But in this case, we just need a little rounded rectangle. It's not complicated. So we insert an operation describing that rectangle, where it is, how big it is, into the GUI operation list. And now we're working with the space defined by the interior of that rectangle. Then we want to make it blue. We're trying to draw a button after all. So we're going to set our paint material to blue. Now the material is a concept pretty similar to when you're working in an image editor. You know, you've got like a paintbrush tool and you configure, hey, I want to paint, you know, red next time I use the paintbrush. So setting the paint material doesn't actually change the visuals at all. It just changes what happens the next time you use the paintbrush. So in this case, setting the paint material to a solid blue, you can envision as a invisible and infinitely large plane of the color blue that if we are to issue a paint, everywhere it intersects with our current clipping area will become blue. And so the next thing we do is paint, and the interior of our selected area becomes blue. For those of you who do GPU programming, you can probably see how this all kind of translates into shaders. This paradigm is intended for it to be easy to understand how to do it, but also efficient to execute this model on a GPU. So now that we have the outline of a button, that's not sufficient. We want to make it do things. So to make it buttony, we need to declare that it is a button. You know, tell the OS, like, hey, this part of the screen, you can interact with it. And we need to say, hey, it accepts pointer input of these kinds. And so we insert operations that work on the current clipping area, right? Everything's sort of relative to whatever we have clipped right now. And that's nice. It gives you sort of a unified topology for thinking about the structure of your UI. So we say, hey, it's a button. It accepts pointer input. And then we want to show some text on our button. Well, how do we do that? We use the same paradigm. We need a clip that describes the shape of the text glyphs that we want to display. So there's a component in GUI that is the text shaper, and it performs a lot of work. It takes a string and it takes a description of the font that you want to use, and it goes through a long process to transform that string into a complex path describing the outlines of those letters. And once we have that path, we just do the same thing we did with our rectangle, right? We clip the path, and then we set our paint color to a solid white, and then we issue a paint. And everywhere that infinitely large plane of solid white intersects with our path becomes white. Same model, same idea. And then when we're done drawing that text, we dismiss the clip because we don't want everything we do from here on out to be limited to the interior of that text, and we're done with it. Note that we have not dismissed our clip of the rounded rectangle, and that's going to matter. So we want to animate. We have that click animation you saw earlier, a circle that expands. So it's a simple idea. We're doing this one frame at a time. So we think about how long has it been since the click event actually occurred, and then we're going to place a circle somewhere within our button, wherever the user clicked, and the size of that circle and the opacity of the circle are going to vary with how long it has been since the click occurred. So we select the location of the click, and we build a clip area of a circle, and we just do simple math. How long has it been? Choose some maximum duration for the animation, interpolate however you want. And we select the circle. We set a paint material, and this time we're going to adjust the opacity of that color based on how long it's been. But it's the same idea. We set the paint color, and then we paint it. And now the interior of that circle is the translucent white that we've chosen. And then we're done with our circle. But you might be wondering, well, as the animation goes, the circle gets bigger. What happens when the circle gets larger than the rectangle it's inside of? You don't want your animation to go outside of the button. And that's why we still have the rounded rectangle clipped. Clipping actually forms a stack. So everything that you've clipped is logically intersected. And for something to be displayed, it has to be inside of all active clips. So when the circle exceeds the boundaries of this rectangle, the area outside of the rectangle is just ignored. You can't draw into it. So then we dismiss both our circle and our rounded rectangle so that we can draw other parts of our UI. If we left the rounded rectangle clipped, we couldn't draw anywhere else. That's what it takes to make a simple button. And you can see it's not complex. I'm not saying that this is the best animation or anything. It's a very simple animation, but it's actually quite easy to build. Okay. So you can use these techniques to build all kinds of stuff. This is just the widgets that we kind of ship in core, and there's a whole bunch of community built ones. I'm going to be teaching a workshop today at 4 on concretely how to do this stuff in code if you'd like to try it. Also, it's kind of an ambitious project to build this sort of cross-platform GUI toolkit. So if you're interested in helping, we'd love for you to reach out. Here are some resources for finding our community. This QR code takes you to this presentation. We have a Slack channel, and we have a mailing list that you can join. You're welcome to reach out to me directly. And there's some links down here to the various projects that I screenshot earlier in the deck, if you're interested in checking those out. Thank you very much. It was an honor to be here.
My question would be, you said that you redo layout on every single frame, basically. Do you also reshape the text on every frame? Because I imagine that would be pretty costly.
No, we do not.
And how do you not do it?
It's not extremely difficult to cache text shaping, and you can cache it at various granularities. When you decompose the text into, say, runs of what scripts it supports or by font coverage, you can cache the results of that. And then if the maximum line length hasn't changed, you can actually cache the results of line wrapping entirely. So you can, if the contents of the text and the constraints haven't changed, you can just kind of reuse exactly the same path that was generated for the previous frame, and is already resident in GPU memory. If the constraints have changed or the text content has changed, parts of the shaping process have to be redone, but not all of it.
Okay.
Just a short one. While mentioning being cross-platform. You at the end said bare metal, but then didn't finish the thought.
Well, there is Elias, the guy who made the project, has a sort of version of GUI that I don't think he's like working on a lot, that runs like on bare metal in QEMU with some interesting like Go runtime shenanigans to make that work. But I think it's doable in theory, and he's got sort of a prototype, but that's not an aspect of the project that a lot of people are focused on. So it's not currently receiving a lot of attention.
We only have time for Martin. You have a question for Chris?
All right, I have a question. When you render the button and when you have the click, the UI layer needs to retain some state, namely like when did the click happen, like in which frame? How do you manage this state? Is the UI a reducer that outputs a new state, or how do you do it?
The UI does have state. The state is just not positional. Like the information that we track is retained in the sense that, you have a widget and it tracks when was I clicked and what was the coordinate that I was clicked. But it's not like a reducer architecture in sort of the functional programming formal sense, because Go is not that paradigm. But we track the minimal state necessary to preserve what widgets do across frames, and we generate the positional and spatial information at layout time.
Thank you.